Thanks, everyone, very much for joining us today for our virtual colloquium this week. I'm Ryan Hickok. I think I know most of you. We're delighted this week to be hosting Professor Vivienne Baldassare from Washington State University. She's just started on the faculty there this fall. This is an interesting time to be starting as a faculty member, but apparently it's going very well. She does some really exciting research looking for objects sort of on the cutting edge of our understanding in terms of the mass range of black holes that we know about. So she searches for, as she will tell you, about the smallest supermassive black holes. Professor Baldassare was an undergraduate at Hunter College, and then did her PhD at the University of Michigan, working with Elena Gallo. She was then, for a few years, she was an Einstein Fellow at Yale, working with Marla Geha, and she knows a number of members of our group through her time there, which is great. Currently, she has the very fancy sounding title of William Band Distinguished Assistant Professor of Physics at Washington State University. And so she's going to tell us today about the search for the smallest supermassive black holes. And so Vivienne, please take it away.
Thank you, Ryan. I'm really excited to be able to tell you all today about my research. So I'm at Washington State University, which, if you're not familiar, is the other big state university in Washington. We are on the complete other side of the state from University of Washington. So I'm about 7 miles from the border with Idaho. But if you've never been to the eastern side of Washington, it's very beautiful. So hopefully once the pandemic is over and can travel again, that will be possible. But it's been really nice moving out here and been managing to enjoy it, even though it's been strange times. So today I'll tell you about some of the work that I'm doing on the smallest supermassive black holes. And to start out, if you followed the Nobel Prize this year, then you've probably seen this video or some version of it. But we know that basically every relatively large galaxy has a supermassive black hole at its center. And when I say big galaxy, I'm talking about galaxies roughly the size of our Milky Way and larger. And of course, in our own galaxy, we have been able to determine the presence of the supermassive black hole by tracking the orbits of individual stars at the center of our galaxy. And based on their orbits and the speeds with which they're orbiting, determine that there is a central mass there weighing about 4 million times the mass of our sun. In other galaxies, this is not possible to do, but we have lots of other evidence for black holes at the centers of big galaxies, and you've probably also seen this image of the center of M87, which is a giant elliptical galaxy, much bigger than our own Milky Way. And this, of course, is the image from the Event Horizon telescope, where they managed to take this picture of the shadow of the supermassive black hole there. And in other galaxies that are more distant, we have been able to determine the presence of supermassive black holes by tracking the bulk motions of stars and gas at the centers of galaxies. And so over the course of several decades, we've been able to determine that basically every relatively large galaxy where we've looked, we have found a supermassive black hole. On the other hand, the situation is much less clear for small galaxies. So this is a picture of the Large Magellanic Cloud, which is a dwarf galaxy in our local group. So it has a mass in stars that is about a few percent the stellar mass of the Milky Way. And as you can see in the picture, it's kind of irregular looking. And one of the things that makes it really hard for these dwarf galaxies is that it can be really difficult to know where to even look for a potential central supermassive black hole. And even though the Large Magellanic Cloud is one of the most nearby dwarf galaxies to us, we don't know whether the system has a supermassive black hole at the center. And so there's a lot left to learn about these dwarf galaxies and whether they contain supermassive black holes like bigger galaxies do. One of the reasons that we're interested in looking for black holes in dwarf galaxies is that they may be a good place to search for intermediate mass black holes. So generally, when we talk about black holes in an astrophysical context, they come in one of two kinds. We have stellar mass black holes that form when massive stars die. And so these can be anywhere from a few to about 100 times the mass of the sun. And then we have supermassive black holes that are at the centers of galaxies. And these are generally upwards of about 1 million times the mass of our sun. And then in between, there's this gap where we think there may be these intermediate mass black holes. But basically, we haven't really found anything between 100 and about few tens of thousands of times the mass of the sun. And so based on the typical ratio of supermassive black hole mass to galaxy mass, we think that dwarf galaxies may host intermediate mass black holes. Recently, LIGO found an intermediate mass black hole through the detection of gravitational waves. So the LIGO intermediate mass black hole sits down there at about 150 solar masses. And then I'm interested in coming at this problem from the other end, which is to look for black holes in dwarf galaxies around 10,000 to 100,000 times the mass of the sun. So the LIGO results and some of the work that I do are both addressing this intermediate mass black hole question, but from two different ends of the mass gap. Some folks are also interested in black holes in dwarf galaxies as they may inform models of black hole seed formation. So we think that the seeds for today's supermassive black holes formed in the very early universe, and there are generally two main categories of theory for how this might happen. One is the heavy seed models, the other being light seed models. And basically heavy seed models say that a supermassive black hole seed could form through the direct collapse of a very massive gas cloud, which would leave behind a black hole that starts off at about 10 to the 4 or 10 to the 5 solar masses. This requires very special rare conditions that may or may not actually occur in the early universe, but would give a way of forming a black hole that starts off very massive. The light seed models predict that these black holes could form through the deaths of very massive stars in the early universe and leave behind a black hole that starts off at maybe 100 solar masses. And this process would be very common. And this simplified picture, it's been suggested that the fraction of today's galaxies, of today's dwarf galaxies that contain a black hole may be able to help distinguish between these two formation channels. So on the left is just a cartoon of the black hole occupation fraction. So this is the fraction of galaxies with a black hole versus the galaxy stellar mass. And the key thing here is that above about 10 to the 10 times the mass of our sun, no matter how the black hole seeds formed, you expect every galaxy to have one. Whereas for low mass galaxies, you start to see a difference depending on the dominant black hole formation mechanism. And these differences might also be reflected in relations between the mass of the black hole and the mass of the galaxy and other scaling relations. So some of the questions that I'm interested in addressing are what fraction of low mass galaxies contain a massive black hole? or contain an active massive black hole, which I'll talk more about. What are the masses of these black holes and how do they interact with their host galaxy? Do they impact the host galaxy evolution in any way? And then how can we potentially use them to learn about black hole formation and growth? So as I mentioned, when we search for supermassive black holes, we are looking for the influence that the black hole has on the stuff around it. And that could be the stars around or the gas around it. And if the system is very massive or nearby, then we can usually look for a black hole by looking at the motions of stars and gas near the center of the galaxy. It's more difficult for dwarf galaxies because the black holes are correspondingly less massive and thus harder to detect. And so for these systems, we can generally only detect a black hole if it's active. So this means that it has a black hole that is accreting very rapidly, and that accretion disk is heating up and emitting lots of radiation and allowing us to detect the black hole at the center. So for systems that are far away or for dwarf galaxies, in order to search for supermassive black holes, we have to search for the ones that are active. So we would really like to find black holes in low mass galaxies. They might teach us about black hole formation in the early universe or serve as analogs to early galaxies. They're unfortunately very difficult to find as the gravitational sphere of influence of a black hole that is 100,000 times the mass of the sun is difficult to resolve even with our best telescopes. And so to find these black holes in dwarf galaxies, we have to search for active ones, which are called active galactic nuclei. Okay, so the field of active galactic nuclei in dwarf galaxies has really taken off in the last 15 years or so. And so as recently as 2004, we knew of only 2 examples of active galactic nuclei in dwarf galaxies. These are the galaxies shown on the right, NGC 4395 and POX 52. So these were serendipitous discoveries of AGN in dwarf galaxies. And for a while, these were the only 2 examples that we had. Thanks to large-scale surveys that have taken observations of tens of thousands of dwarf galaxies and multi-wavelength efforts, we're starting to make a lot of improvements on this. So it's been a really exciting field to be a part of. But it's really been a field that's taken off very recently. Just to give a little background on some of the signatures that we look for when we search for active galactic nuclei. This is a cartoon of an active galactic nucleus that I made for my PhD thesis. You have your black hole at the center being fed by an accretion disk of material. There is gas nearby in the broadline region, which is close enough to the black hole to be influenced by the gravity of the black hole. This gas is photoionized by photons from the accretion disk. And then basically you get these Doppler broadened emission lines since that gas in the broadline region is roughly orbiting around the black hole. Gas in the narrow line region is also ionized by photons from the accretion disk, but is far enough away that you don't get the same Doppler broadened emission lines. Then we also think there is some kind of obscuring torus around the black hole and accretion disk and the broadline region, such that you don't always see the broadline region gas depending on your viewing angle. There's also an X-ray emitting corona surrounding the accretion disk, and sometimes jets, which are visible at radio wavelengths. So this is often a very multi-wavelength endeavor. And this is just an example of an optical spectrum of an active galactic nucleus. You can see some narrow emission lines from the narrow line emitting region. And then you also get these broad Balmer emission lines from the broadline region. And the width of those lines tells you something about the typical velocity of the gas in the broadline region. And AGN are often selected through these emission line signatures. So this diagram is called the BPT diagram, and these particular ones are from work by Amy Rines in 2013. And basically, the BPT diagram uses the relative strengths of emission lines to characterize the dominant source of photoionization in a galaxy. So you plot the relative strengths of these emission lines, and it tells you whether your galaxy has an active galactic nucleus, or has gas that is being ionized by recent star formation, or some composite combination of the two. And so this particular work looked at 25,000 nearby dwarf galaxies. So these were galaxies that had stellar masses less than or equal to that of the Large Magellanic Cloud, which is the dwarf galaxy example I showed in the beginning, a few percent the stellar mass of the Milky Way or so. And of these 25,000 galaxies, they found about 150 that had these narrow line ratios suggesting the presence of an AGN. So that's the figure shown on the left. And though that may not sound like a lot, this was a huge jump in the number of dwarf galaxies that we knew to contain active galactic nuclei. One of the problems is that these diagrams were designed for and partially calibrated with higher mass galaxies, and so may not always select all of the AGN in dwarf galaxies. So there are a couple of potential issues with selecting just based on these optical spectroscopic diagnostics that mean you may not catch all of the AGN. And although they might be reliable in that things that are classified as AGN are genuinely AGN, we might be missing some. So in dwarf galaxies, low metallicity or strong star formation can mean that objects might not show up as AGN on this diagram. So the plot on the right here is the same X and Y axes as the previous slide. And what these tracks are showing is how a galaxy would move on this diagram if you shifted it towards lower metallicity, where metallicity is just the fraction of elements that are not hydrogen or helium in a galaxy. Dwarf galaxies tend to have lower metallicity than higher mass galaxies. And so as you decrease metallicity here, even something that has an AGN may not show up as an AGN using these diagnostics. And then dwarf galaxies may also have star formation, which is strong enough to dilute the relatively low luminosity signal from a low mass AGN. And so we may be missing some AGN in dwarf galaxies. So we'd like to find other ways of looking for these systems. Another property of active galactic nuclei is that they tend to vary on human timescales, so days to years. Instabilities and turbulence in the accretion disk that is feeding the black hole lead to variations in the light output from the center of the galaxy over time. So the plot on the right here is just showing the brightness versus time for a very well-studied AGN over the course of 8 years. And you can see that the flux from this particular AGN is varying by about a factor of 2 over this time period. These variations tend to be aperiodic, and we observe them basically at every wavelength on a wide variety of timescales. And it's exciting because right now we're in a really golden era for time domain astronomy. There's a lot of currently publicly available repeat imaging surveys And soon the Vera Rubin Observatory will begin operations with their legacy survey of space and time. And so there's just a wealth of repeat imaging data that we can use to look for this variability as a way of detecting active galactic nuclei. And so what I'm interested in doing is using this optical photometric variability to find active galactic nuclei in low mass galaxies. So my first effort to do this used a survey called Stripe 82, which was run by the Sloan Digital Sky Survey between about 1998 and 2008. So Stripe 82 is a roughly 300 square degree region of the sky. And what I did was to reprocess the Stripe 82 data and look at a sample of 28,000 galaxies within this region of sky to search for variability. So these galaxies spanned a wide range in stellar mass and were relatively nearby. And the final light curve length was about 6 years with a median number of data points of 17. And then I looked for AGN-like variability around the center of the galaxy. In order to detect this kind of low-level variability on top of a background of a host galaxy, you really want to be able to subtract off the light from the host galaxy so you can better detect any potential nuclear variability. And so to do this, I use a technique called image subtraction or difference imaging. I'll walk through just a couple of the basic steps here. The first thing that you want to do is to construct a template image from your best quality frames, so your sharpest seeing and lowest background, and combine them to create a really high quality image. And then what you basically do is degrade the template image to match each individual exposure, to match the resolution of each individual exposure, and then subtract the two. So you're left with a relatively flat difference image unless you have some kind of variable source, which will then pop out against the background as a dark or light point, depending on whether it's gotten fainter or brighter relative to the template. Then using forced photometry at the position of each of these 28,000 galaxies, I constructed a light curve by measuring the light within a 2.5 arcsecond aperture centered around the nucleus of the galaxy. I then searched for variability that was AGN-like by determining the goodness of fit to a damped random walk model, which has been found to be a good empirical descriptor of AGN variability. So this here on the right is an example of a galaxy that was not found to be variable. So the top image is just the galaxy with the aperture for photometry on top of it. And then below is the light curve for the galaxy, so showing the brightness over time. That's the gray circles. And then the damped random walk model is the blue line with the model uncertainties given by the blue shaded region. But this galaxy was not found to be variable. Oh, sorry, that should play. So you can see in the little animation of the difference images that there's really nothing happening there. It's just noise. This is then an example of a galaxy that was found to be variable. So you can see in the light curve that there's lots of variability, and it's also well described by this particular model for AGN variability. And then in the difference images, here it's a very obvious case where you can see the central source varying over time. So in the Stripe 82 sample, I found 35 low mass variability selected AGN. So these are a couple of examples on the left. The top galaxy has a stellar mass of a few times 10 to the 8 solar masses. The one on the bottom is about 10 to the 9 solar masses. Of the full sample, there were 135 galaxies with AGN-like variability, and then 35 of these were low mass. The full sample is plotted there on the histogram in gray, and then the variable AGN are shown in orange. So they tend to skew towards the higher mass galaxies in the sample. But nonetheless, we did find some low mass objects, and so this was encouraging and led me to carry out a bigger hunt for variable low mass AGN using data from the Palomar Transient Factory. So this is a survey that ran from 2009 to 2017, has now been converted into the Zwicky Transient Facility. PTF covered about 30,000 square degrees of sky. You can see the sky coverage map on the right there. And the color coding, it's hard to read the numbers, but it goes from 0 to about 7,000. So there are some areas of the sky here that were covered thousands of times. And here I looked at a sample of about 50,000 galaxies, primarily low mass galaxies with stellar masses less than about 10 to the 10 from a sample called the NASA Sloan Atlas. And just to compare to the previous work, this sample contained 35,000 galaxies below 10 to the 10 solar masses within this redshift of 0.055, compared to about 5,000 from the STRIPE 82 sample. And though the typical light curve baselines here were shorter, the number of points in any given light curve was greater. So from this Palomar Transient Factory sample, found 250 variability selected low mass AGN. So these are a couple of my favorite examples from this work. The one on the left is the lowest mass galaxy that was found to have some AGN-like variability. And then the one on the right I like because it's got kind of an interesting morphology with this off-centered knot there. I also wanted to look at the optical spectroscopic properties of these galaxies. So this is, again, the BPT diagram, which allows you to classify your galaxy as AGN based on its optical spectroscopic line radios. And on this plot, I'm showing all of the galaxies that were found to have AGN-like variability from the Palomar Transient Factory sample. The points are color-coded by galaxy stellar mass. So the highest mass galaxies are yellow here, and then the lowest mass galaxies are the pink and purple. And what I found is that while basically all of the high mass galaxies with AGN-like variability fall in the AGN or composite region of this diagram, for the low mass galaxies, most of them fall in the star forming region. So what this is telling us is that the variability selected AGN with star formation dominated narrow lines are AGN that are potentially missed by other selection techniques. So these low mass AGN that have variability suggesting the presence of an AGN would not have been selected as such based on the standard optical spectroscopic diagrams. So we're potentially finding this sample of missed AGN in low mass galaxies. All right, so that's great, but what can we do now with these samples of low mass AGN we're building? Well, this is not necessarily related to low mass, but one of the things that I looked at was the fraction of variable AGN as a function of baseline. And I just think this is something important to consider as we approach the start of operations for LSST, is that the fraction of variable AGN that you'll measure is dependent on the baseline of your observations. So you can see that for this sample, as you increase the baseline from 1-ish to 6 years, the fraction of variable AGN that you detect increases. So if you're comparing the fraction of variable AGN across samples, you want to make sure you're controlling for baseline. One of the things that I was really excited to look at, though, was the AGN fraction as a function of stellar mass. So this is the variable AGN fraction as a function of galaxy stellar mass. And from this, you can see that the fraction of variable AGN is increasing as you move towards higher mass galaxies. The red shading there just reflects where we were incomplete in terms of stellar mass. On the right is a histogram showing the distribution of stellar masses for the full sample in gray, and then for the variable AGN in blue. And so again, they skew towards higher mass galaxies. However, we also see that the variable AGN fraction is a strong function of the nucleus magnitude. So on the right there is, again, variable AGN fraction versus basically the brightness of the nucleus, where brighter objects are on the left and then fainter objects are on the right. And basically, it's harder to detect lower levels of variability in a fainter galaxy nucleus. And since the dwarf galaxies in the sample are fainter, we have to control for this if we really want to compare the fraction of variable AGN in different stellar mass bins. So in order to do this, I basically made brightness matched subsamples in order to properly compare the fraction of variable AGN in different stellar mass bins. So the histogram on the left there is showing the magnitude distribution for high mass galaxies in the sample in gray, and then galaxies between 10 to the 9 and 10 to the 10 solar masses in red. And so then I would draw subsamples from the red histogram to match the magnitude distribution of the higher mass sample. So one instance of that is shown as the blue hatched histogram. And when matching for the magnitude differences, what I find is that for high mass galaxies, the fraction that contain a variability selected AGN is about 1.5%. And for galaxies between 10 to the 9 and 10 to the 10 solar masses, the fraction of variability selected AGN is consistent with that. So down to about 10 to the 9 solar masses, after controlling for magnitude differences in the subsamples, you get that the fraction of variability selected AGN is constant. For galaxies at the lowest masses, so below 10 to the 9 solar masses, the fraction does appear to drop, but there is an issue where the Sloan Digital Sky Survey is incomplete for these galaxy masses. And so it's basically hard to say whether a fraction truly drops or if we're just missing a whole bunch of galaxies here or simply not able to detect variability from the mass of black hole that would exist in these systems. So I think there's still a lot of work to be done for these lowest mass galaxies, but at least down to 10 to the 9 solar masses, the fraction of variable AGN is constant, which could suggest that the overall fraction of galaxies that contain a black hole is not terribly different down to that stellar mass. Okay, so why are we missing most of the low mass AGN with these optical spectroscopic diagrams? A couple of the reasons that I discussed are low galaxy metallicity or star formation dilution. But in order to figure this out, I think we need to compare galaxy properties of these different ways of selecting AGN. So Here I'm just showing the G-R color of the variability selected AGN. So those are shown in blue, and then those selected through optical spectroscopy in purple. So those are the Ryan et al. 2013 objects. And the variability selected AGN do seem to be bluer, which could suggest that it's a star formation dilution issue. But there's definitely work to be done here in terms of comparing galaxy properties. So I had a Cycle 22 Chandra X-ray Observatory and Hubble Space Telescope program approved to look at a subsample of these low mass galaxies with variability selected AGN to both search for X-ray emission to provide confirmation of the presence of AGN in these systems, and then to characterize the host galaxy morphologies and star forming properties. So this will help in both studying the AGN as well as determining if there's anything that sets these galaxies apart from the dwarf galaxies with AGN selected through optical spectroscopy. I wanted to just touch on a couple of other short related projects. So my quarantine paper for this year was looking at the low mass end of scaling relations between the black hole and host galaxy properties. So one thing that I looked at was the M sigma relation, which is a relation between black hole mass and the stellar velocity dispersion of the host galaxy. This was the sample that we looked at. So these are galaxies selected from Ryan et al. 2013. They all have AGN or composite narrow line ratios, and they all had these broad emission lines from which we were able to estimate the black hole mass. And this shows the M sigma relation. So again, this is the relation between black hole mass and host galaxy stellar velocity dispersion. This relation is very tight for high mass galaxies, but relatively unconstrained at the low mass end. And so the dwarf galaxies with AGN that we measured new stellar velocity dispersions for are shown in red down there. And basically what we find is that these dwarf galaxies agree with the extrapolation of the M sigma relation to low galaxy masses. So these are the new objects that we were able to add to this sample here. In the variability work, I've also had a lot of fun looking at things that are not AGN at all. So this was kind of a neat side project led by Colin Burke, who's a grad student at UIUC. And this little object, PHL293b, is an extremely low metallicity dwarf galaxy that both Colin and I had found to have variability that looked very AGN-like. So those are shown on the bottom there. Those are G and R band light curves. And we combined data from my analysis with Stripe 82 and Colin's analysis using the dark energy survey data. So we found this galaxy to have variability that was kind of AGN-like. And this galaxy also had a broad emission line in its Sloan spectrum taken in 2001. So that's shown on the left. There were a lot of spectra taken in the intervening years where it still had a broad emission line, but detecting this variability from it encouraged us to get a new follow-up spectrum with Gemini last year, and we found that finally the broad emission line in this object was starting to fade. And so this was a real puzzle to work out, but we explored a lot of different possibilities that could explain this low-level variability, as well as this broad line, which was persistent for 10 or 15 years before finally fading. And we the best explanation that we could think of was some kind of very unusual, long-lived type 2 supernova. So this is just a table from that paper listing out all of the different weird properties for this object and the various explanations that we considered for it, including an AGN or a luminous blue variable or some kind of stellar wind. And so we settled on a very unusual type 2 supernova, but this was a lot of fun. And so with these really big variability surveys, you sometimes end up studying things that you never thought you would, because there's tons of interesting stuff to be found when you're looking at samples of tens of thousands of galaxies. Yeah. All right. So in the last couple minutes here, I just wanted to talk about, some future observations and surveys that I'm a part of, and areas for making progress on some of these questions of AGN and dwarf galaxies. So using the data from Stripe 82 and the Palomar Transient Factory, we were able to get a fairly good constraint on the fraction of galaxies that contain a variable AGN down to about galaxy stellar mass of maybe 10 to the 9 times the mass of the sun. And below that, it's difficult because our galaxy samples are incomplete and we need more sensitive imaging and possibly shorter cadence observations. So observations that are taken more frequently, since we expect lower mass black holes to vary on shorter timescales. And so there are two really neat surveys that I'm excited to be a part of that I think will make progress on both of these areas prior to the start of observations for the Vera Rubin Observatory Legacy Survey of Space and Time. So they are the Young Supernova Experiment and the Merian Survey. The Young Supernova Experiment is a collaboration with PIs at Washington State University, so me, UC Santa Cruz, UIUC, University of Toronto, Northwestern, and the Dark Cosmology Center. The full collaboration is about 60 members or so, and it's a repeat imaging survey using one of the Pan-STARRS telescopes. And we just had our survey paper come out on arXiv, I believe last week, if you're interested in reading more about it. The Young Supernova Experiment is, as you can tell from the name, designed to detect very young supernovae. And so the survey takes deep imaging in 4 bands in a group of relatively well-selected fields, so it's designed to overlap with fields that have a lot of other supplementary data or are being covered by other repeat imaging surveys. But the whole survey area will be about 1,500 square degrees. And while it was designed primarily for detecting young supernova, it will also be really valuable for AGN science and studying tidal disruption events and a lot more. Our collaboration interests are very varied. And just to compare it to some other repeat imaging surveys, it will go a lot deeper than surveys like Assassin or CTF. And then the pixel scale also is much smaller than other repeat imaging surveys, which is great for the kind of work that I do because we'll be able to better isolate any variability from the nucleus. And then the cadence is about 3 days, which will be great for searching for these low mass AGN that we expect to vary on shorter timescales. And the photometric precision is really good, about 3 millimagnitudes. So between the depth and the photometric precision, the small pixel scale and the cadence, I think this is going to be really great for pushing down on the mass of black hole that we're able to detect through variability. The Merian Survey is being led by Alexis Lethode at UC Santa Cruz. It is named after Maria Sibelius Merian, who was a biologist in, I believe, the 1800s, and she is very well known for studying the life cycle of caterpillars and other bugs, and she made a lot of really amazing observations and drawings of tiny creatures. And so we named this for her because we're looking at tiny galaxies, and she was studying other types of tiny things. But basically, the Merian Survey is designed to take a census of dwarf galaxies in the nearby universe. One of the difficulties with building samples of dwarf galaxies is that if we want to measure masses, we have to know how far away they are. Dwarf galaxies are faint, and it can be resource expensive to take spectroscopy and get redshifts for all of these galaxies. So Merian will use 2 custom-built narrow band filters to try to detect star forming or dwarf galaxies with emission lines out to a redshift of about 0.1. And we expect to be able to detect around 100,000 dwarf galaxies with this survey. Observations will be taken starting in February 2021 with DECAM at CTIL. So this will be a great step towards building up larger samples of dwarf galaxies and helping with that incompleteness issue that I talked about. So I'll leave you with some takeaways. We can't observe black holes forming in the very early universe, but clues to black hole formation can be found in today's smallest galaxies. And these also might be a great place to search for intermediate mass black holes. Black holes in these small galaxies are traditionally very elusive, but I think variability is a new and very promising way of detecting these. It's allowing us to start to place some meaningful constraints on the low mass end of the occupation fraction and scaling relations. And new surveys like the Young Supernova Experiment and Merian will allow us to search for much fainter and lower mass active galactic nuclei in the smallest galaxies. And with that, thank you for your time. I'm happy to take questions.
All right, thank you very much. Not sure we can clap with it, but anyway, hopefully you can hear the virtual applause. Great, so we have plenty of time for questions. Anybody of the attendees, if you'd like to raise your hand or put a question into the chat, please do so. So go ahead and raise your hand if you have a question. So while people are formulating their questions, I've got one related to something you said right at the end here, which is that the low mass black holes have a shorter time scale for variability. So I know that you're using a somewhat random, or you're modeling these as a somewhat random process, or it really is a random, well, close to random process, right? But I'm wondering if you see a difference in the typical timescales for variability for the lower mass galaxies compared to the higher mass ones, such that they would correspond to black hole masses consistent with what you're getting from your M sigma relation measurements.
So that's something that I'm actually going to be looking into with the Young Supernova Experiment data. And I haven't really been able, well, with the Stripe 82 and Palomar transient factory data, the cadence wasn't ever short enough to really be able to answer that question as to whether there was a difference between, or a difference with black hole mass. And so what I think will need to be done is to basically take really high cadence light curves of dwarf galaxies where we have an estimate of the black hole mass, and we know it's like 10 to the 5 or 10 to the 6, and see if there is a difference there between them and the higher mass galaxies. Because it would be great if that could be used as a way of getting at the black hole mass.
Great. So we have a question in the Q&A here. Christina, I guess you're welcome to talk if you want to, but I can also just ask this one. Her question was, what is and this is just getting back to the sort of motivation at the beginning, what is a light seed? What really are the distinctions between these different seeds?
Yeah, so there were a couple of different class of theories that I mentioned for how the supermassive black holes in the very early universe might start off. And so there are heavy seed models which predict a black hole starting off at about 10 to the 4 or 10 to the 5 solar masses. And then there's the light seeds which predict that the what go on to become today's black holes start off as about 100 solar mass black holes. So those are the light seed models which predict that what goes on to become today's supermassive black holes started off from the deaths of massive stars in the early universe and were about 100 times the mass of the sun or so. And I think the observations, the numbers of dwarf galaxies that we're finding to contain AGN and the results from scaling relations are more suggestive of this formation pathway than the heavy seed models. Does that make sense?
Christina says yes.
I see in the chat that you say yeah. Okay.
And so Robert Caldwell has a related question, which is he's asking how well can you discriminate between these scenarios? So we're sort of pointing in one direction here. And he mentioned that this seems to be a big source of uncertainty in estimates of the rate of supermassive black hole binary mergers. So do we have, is there another way of framing this? And there was actually at the High Energy Astrophysics Division seminar this afternoon, there was a talk by Fabio Paccucci, who works on simulating this precise thing. In terms of the occupation fractions of the AGN that you see a low redshift, does that inform for us what might be the merger rates sort of earlier in cosmic time?
Yeah, it's complicated, and there's certainly nothing to say that you know, both of these channels couldn't operate in terms of the seed formation, but I think it is suggestive of it not being just heavy seeds, if that makes sense. In terms of mergers and things like that, there have been some theories that suggest that the black hole mass to stellar mass could tell us something about that, but that also depends on how much we think they accrete. I think it will probably not be until LISA that we really get a better grasp on the merger rate. But that I don't think really answered the question, but it's highly speculative.
Well, Robert, that means Robert does a lot of work with LISA. So Robert, okay. That means that
I want to know before.
Yeah, beforehand, exactly.
Yeah. Right. Yeah. There's a lot of cookbookery that goes into it, and it'd be nice to know in advance what the rate is going to be. But
cool. Our next question is from Kelly.
Hi. That was an awesome talk. I was wondering for a second if you can go back to the G-R histogram that you showed of the two samples that you're looking at.
Yes.
Yeah, that one. Okay, I might have missed this earlier. Are these two samples roughly the same mass? Like, do they both just consist of dwarf galaxies, or is the Ryan's one also including more massive galaxies?
No, they're both for galaxies less than 3 × 10⁹ solar masses.
Cool. So why do you think there's a difference in color by the way you're identifying them?
So my thought is that maybe we can, well, so I think it could be related to star formation dilutions. So if the ones that we're able to find through variability tend to be bluer, maybe we're only able to see the AGN-like emission lines in the ones where we do observe them because there's not as much star formation diluting that signal. Does that make sense?
Yeah, thank you so much.
I guess it could also be a metallicity thing.
Great. Have any more questions? I have one last one, which is, you showed that interesting object with the unusual morphology that had like the sort of knot that was off center.
Yeah, this one.
Yeah, so given you mentioned early on that sometimes it's hard to even tell where the center of a galaxy is. So I'm wondering, for the things that have variability that looks like an AGN, how often do you find ones that are not in what looks like the photometric center of the galaxy?
Yeah, that's a really good question. And we generally don't, and that's sort of because of the way that I carried out the search, which was to look in a 2.5 arc-second aperture at the center as defined by the NASA Sloan Atlas. And in some sense, like, that can sometimes be most of the size of the galaxy anyway. But I think what would really be better to do is, I don't, maybe like lay down some kind of grid on top of the galaxy and look for variability in each little section if the goal is to find potentially off nuclear variable sources, which for dwarf galaxies is very possible and interesting. So I think there's a better way to, or another way to search for variable AGN in these objects, which would be more sensitive to off nuclear things. So like for this object with the little knot, that is where SDSS defines the center. And so that, yeah.
Okay. Interesting. Cool. Do you have any last questions? Okay, well, with that, let's all thank Vivienne very much again. It's been really a pleasure having you here in the department today. And those who have been allowed to talk, you can